to sub for Dr. Burns today. I think he took the science club on a field trip. I teach this same course as an adjunct at night on Tuesday nights. Okay, I'm actually about an hour or probably 2 hours behind where he is in this lecture. Okay, but nevertheless, we can take care of this stuff. Okay, I encourage you to ask questions. Okay, if you got them. Okay, I'll ask you some questions. That's just the style of my instruction. Okay, hopefully get you involved. You really don't want to hear me for an hour and a half. One type of voice. So he gave me a kind of set of worksheets that he goes by, kind of a lecture outline. So that's what I'm going to go by. I do it a little differently, but I'm following his format as much as possible. So hopefully I will be able to do pretty much the same stuff of what he does. Okay, so he told me to start with neutralization. So basically when we talk about acid-base neutralization, you take an acid and a base and you yield water as a product and salt, okay? And we use the term generally salt, okay? Not always sodium chloride, okay, but a salt. So one of the classic examples for acid-base reaction could be take your acid like HCl, okay? Hydrochloric acid, of course, it has to be in solution aqueous. You take a base, could be any base, any strong base, which is group 1, group 2 base. Let's use potassium hydroxide. I believe that's what the lecture notes use. Now, you have been studying types of reactions, so you should be aware of double replacement reactions, okay? Basically where the two like anions just simply swap places. And you're trying to get some kind of change. Now, the classic double replacement reaction is where you precipitate a salt, okay? And you got to have your solubility rules and all that other good stuff. Here is a double replacement reaction, and basically what drives this reaction forward is the production of water. And so basically the potassium cation and the hydrogen that acts as a cation switch places, and there's where you get your water, okay, as a liquid, okay, so it's a different form, and then your salt is what's left over. And if you look at the salt in this particular case, it is potassium chloride. And the salt is always, okay, the cation from the base and the anion from the acid. Okay, so that's when you create that salt. Okay, you're always going to get it from the cation of the base and the anion of the acid. Okay, so the cation from the base, of course, is the potassium. The anion from the acid, of course, is the chloride. So you get potassium chloride, and this one is in solution. And so most of the salts do happen to be soluble and are in solution. So an acid-base reaction is a neutralization reaction, okay? It cancels out the strength of the acids, the properties of the acids, the properties of the base, and you get salt and water, okay? That's if they're pretty much similar as far as concentration and strength go, okay? If you throw in a really concentrated with a little bit of a weak one, you get the reaction, but it'll be so strongly in one direction or the other, you won't get, quote, quote, neutralized. Here, if these are about the same concentration and strength and volume, you get a neutralization reaction. You'll cancel out the properties of the acid, cancel out the properties of the base. Yes, ma'am?
Does the H2O on the product side, is that, in parentheses, is that liquid?
It is liquid. Okay?
So what's the difference between aqueous and a liquid?
Okay, so aqueous means it's dissolved. Okay? So this potassium chloride is potassium ions and chloride ions that have been disassociated, right? That are broken down into ions in solution. Here is actually a molecular compound. Okay? So here is those ions dissolved, aqueous. Here is a molecular compound, okay, in the state of a liquid. Okay? Make sense? Mm-hmm. All right, so there's your classic acid-base reaction. Make sense? All right, so now I don't know how he does practice portions, but he's given you 4 or 5 problems in number 15 to practice on. So let's work a couple of them together. Is that what he usually does? Okay. All right, so let's do the first one, okay? So H3PO4, what's the name of that species? Okay, and then more correctly written, it should be AQ, but again, that's the way I would have written it, or wrote it. So what's the name of that species, H3PO4? Okay, it's phosphoric acid. Okay, hydrogen phosphate would be the compound, but when you put it in water, it's called phosphoric acid. Okay, all right, it's reacting with KOH. Okay, and of course, this is also aqueous, and the base, of course, is potassium hydroxide, like we had here. All right, so if you think about and look at the format of my practice example, okay, let's kind of understand what the salt is first, okay, and the water, and then we can worry about balancing the equation, because again, at the end of the day, all equations got to be balanced. So, everybody agree that I'm going to make water here, okay? So, water is going to be one of my products, and then what is my salt going to be? Okay, the cation from the base, the anion from the acid. So what is the salt going to be? The cation from the base is, of course, the potassium ion. Okay, what's the charge of a potassium ion? Okay, it's in group 1, so it's always +1. Okay, get rid of this marker. Okay, and then what is the anion from the acid? It's the phosphate ion, PO4 ion, and what's the charge of the polyatomic PO4 ion? -3, okay? And so that's -3. So now what do the sum of the charges have to equal in a compound? Okay? Sum of the charges in a compound have to equal 0, right? So how do I write that correctly to make the sum of the charges equal 0? Make a subscript of a 3 here, so make it K3PO4, okay? So now it's written correctly. Once everything's written correctly, and that's what I harp on my folks about, you've got to make sure that you understand those ions correctly, okay? Once you got it correctly, now you can work on balancing, right? Satisfying the law of conservation of mass, correct? So, help me balance it. What would I do, please? Put a 3 in front of the KOH, it's called a coefficient, right? All right. And 2 in front of the H2O. And does that balance it? Does that get it balanced? So if you look at, I got 3, okay, and 3 more hydrogen, 6. It's not going to work, okay? I got 2 times 2 is 4 plus 4 over there is 8, okay? So, you know, the hydrogens, okay, 6 is not going to work with that. So that's not going to work. I don't necessarily disagree with the 3 right there. I think that's good, okay, because that balances out the potassium, but the 2 is not going to help the H2O. So put a 3 in front of the H2O. Now 3 times 2 is 6, okay, and 3, and then 3 more for hydrogens is 6. That's good. So now let's continue with the rest of it. Again, the way I balance equations is I put, if it's a polyatomic ion on both sides, I try to group it together. Okay? One of the general rules to help you balance equations. So I'm going to look at that PO4 as one group. The PO4 is one group. There's 1 on each side. It's good. Potassiums are good. Okay? The hydrogens are good. And so the oxygens should be good. Should be balanced like that. Okay? Should be balanced like that. Anybody have an issue with that? Questions? All right, let's look at the third one. Okay, H2SO4. What's the name of H2SO4? In solution. So it's called sulfuric acid. Hydrogen sulfate called sulfuric acid. Okay, what would be the name of the next compound? Say it again. Okay, titanium hydroxide, and since titanium is a transition metal, we're going to put a Roman numeral to indicate its oxidation state. So probably going to be named titanium 4 hydroxide. okay, because it gives you an idea of the oxidation state. All right, so acid-base reaction, okay? Here's your acid, here's your base. You know you're going to make water, so that's pretty easy to figure out, okay? And then if the cation, the salt is the cation from the base and the anion from the acid. So what's your cation? Titanium. Is it going to change oxidation states? No, this is not a redox reaction, okay? So it is going to be titanium and it's going to be a positive 4 charge. I like to put the charges there that helps me write the equation correctly, okay? And then what is your anion from the acid? Okay, the sulfate, SO4, and what's the charge of a sulfate anion? It is -2, okay? So how do I write the formula for that particular salt correctly? Okay, encase it in parentheses. The gentleman was back there was doing some kind of hand motion, I think, to say encase it in parentheses, okay? And then put the 2 there, right? So that makes sense. Now we're basically got everything written correctly, okay? Now we're ready to do the balance, the mass balance, okay, or this law of conservation matter. What do I do? What do I do to make this thing work?
2 in front of the H2SO4.
2 right here.
And then a 4 in front of the H2O.
Okay, and a 4 right here. What's your name?
Hampton.
Sir?
Hampton.
Hampton. Okay, so Hampton's going to do like so. I'm going to look at the SO4 units together. There's 2 of those. There's 2 of them over there. That looks good. Okay, I got a total of 4 hydrogens. Okay, and I got a total of 4 more. Okay, hydrogens here. So 8, 4 times 2 is 8. That's going to work out. Titanium is going to work out, and then the oxygen is going to work out. So that is correct. Good job. Okay, and the gentleman back there giving me the parentheses signal. Good job. Okay. Make sense? Make sense? Let's do that last one just to make sure. You do it on your own. H2CO3. What's the name of that? Anybody know? H2CO3. Carbonic acid. When you put it in liquid, it's carbonic acid. And that is uranium hydroxide, UOH6. Give that one a shot. Take your time, make sure you write the formula of the salt correctly, and then it'll make it a whole lot easier to balance. Give you another minute or so to try to work that out, and then we'll look at it and move on. Ma'am.
What's uranium's charge?
Okay, so what's the charge of hydroxide? -1. So the uranium has to be what? In order for that UOH6, if this is -1, then remember the sum of the charges has to equal 0. The uranium has to be what? Has to be +6 in order for that to work out. So the uranium is +6 in this particular example. Okay? That make sense? Okay. Okay, so what's going to be the formula of the salt that's created here?
U parentheses CO3 parentheses 3.
So it's going to be uranium. It's going to have that still. It's going to have that positive 6 charge. The CO3 negative 2 ion comes from the carbonic acid. Okay, and you got to encase it in parentheses because you're going to use it several times. How many times are you going to use it? You got to use it 3 times, so that you have negative 6 corresponding to the positive 6. So the sum of the charges is equal to 0. Okay. Again, if you can't get your salt written correctly, it's probably not going to work out very good for you. Okay? All right, now we're ready to balance. Please do so.
3 in front of the H2CO3.
All right, so hold on. 3 in front of here. Somebody help Hampton out and give me the rest of it.
6 in front of the H2O.
6 in front of the H2O. Somebody else, tell me, is it balanced if I do what those folks told me to do with coefficients? Okay? Should be balanced. If you count it out, it should be balanced. Uranium, 1 on each side. 3 CO3 groups. There's 3 CO3 groups. And then if you count the rest of the stuff, it'll balance out the hydrogens and the oxygens. Any questions? Okay, so you got one left to do on your own. There is a different type of acid-base type of chemistry. If I take an acid and a base that's similar to ammonia, okay, what I create is a salt. Okay, no water in this one. So here, if I take HCl, okay, as an acid, if I take the base NH3, which is ammonia, okay, basically what happens is the cation from the acid, okay, makes a complex with the ammonia, makes, in this case, the ammonium ion, okay, which you should have learned is ammonium positive 1 polyatomic ion, okay, and then the chloride is left over as the cation, and so there's your salt. An ammonium type complex or a nitrogen bonded with that extra hydrogen type of complex, and then whatever anion is left over from the acid. So no water involved when the base is an ammonia-like substance. Okay, so a couple of examples they give you there, okay? The first one is ammonia and H3PO4, okay? Everybody good with this? Can I erase? So NH3 plus H3PO4, okay? So if I look at this, okay, and again look at it from this particular point of view, okay, what I'm going to do is I'm going to produce an ammonium ion, okay, and I'm going to produce take the acid and use its anion, which in this case is what? Phosphate, PO4, negative 3 charge, okay? So now I'm going to write the formula for the salt correctly. How do I do that? Okay, I got to use 3 of these ammonium groups, so polyatomic used more than once is encased in a parentheses. And so the ammonium phosphate is written as so for the salt. Now I worry about balancing it, okay? If I understand the concept of what's going to happen, now I should be able to just balance it, okay? So, help me balance it. What do I do, please?
Put a 4 in front of the H3.
Put a 4 here? Is that what you said?
Yeah,
Okay?
maybe.
So let's see if that works. If I have a PO4 group, I have a PO4 group. Remember, try to leave your polyatomics the same if they're on each side. So that will work. 4 nitrogens, okay? Only got 3 over there. Okay? Now that's written correctly. Can we just try a 3 here instead of a 4? Because now I got 3 nitrogens. Here I've got 3 nitrogens, correct? And then 3 times 3, 9, plus 3 more, 12. 4 times 3 is 12. It works that way, okay? So I think the key to doing these correctly, okay, is to understand the concept, okay, of generally what happens, okay, understand how that quote, quote, salt is made, okay, cation from the base, anion from the acid, okay. This one again is the ammonium plus the anion from the base. Write the formula correctly and then worry about balancing later on, okay. Do it step by step, my philosophy. Questions? All right, so let's look at the second one, okay? H2CO3 plus the ammonia, okay? H2O3 is the carbonic acid plus the ammonia. So what kind of salt are we going to produce? What kind of salt are we going to produce? An ammonium salt, okay? And then the anion from the acid, which is going to be carbonate, CO3. What's the charge of CO3? -2. Again, to write this correctly, what do I got to do? Case it in parentheses and put a 2. Okay, so now if everything's written correctly, I should be able to rock and roll and balance it. Please help me do so.
Put a 2 in front of the NH3.
Is that all it takes? Okay. The last compound is a little different. It's called pyridine. Okay. The last compound is called pyridine, C5H5N. Okay. Plus the HCl. Write it correctly, it will help. This one is a little different, okay, because this now, because it has the nitrogen in there, acts as quote unquote an ammonia-like substance. And so basically what happens is you get C5H5NH as a cation. And basically, it's the same thing that happened with all these things. The hydrogen part of the acid went towards the nitrogen. That's the same thing that's happening here. The hydrogen part of the acid went towards the nitrogen compound to make a cation. Okay? So that's what that is. And of course, then what's left over is your anion, the chloride. That one is, my opinion, okay, a little bit maybe out of what I would choose as the realm for this one, okay? But it does work. Sorry.
Are these reactions like both ways, or?
No, these are in one direction only, okay? These are not usually reversible reactions, okay? Is that what you're asking?
Yes.
Yes, sir. Yes, ma'am.
Why is the H on the other side too?
Okay, because the HCl breaks down and the H goes towards the nitrogen, okay, so makes that a cation, okay, just like it did here. Remember, we had the NH3. Really, the H here is migrating over here, so it's the same type of principle. Okay, again, to me that one's a little beyond scope, but he asked me to share it, and I shared it. Questions? Okay, generally okay, balancing equations. First page. All right. So now he talks about this concept called electrolytes. I don't think you've done this in lab yet. I think it's this week or next week you do this in lab. But you're actually going to look at this. When I teach this next week in my class, I will actually bring in an electrolysis demo. That's what I like to do. I should have brought it, but I didn't. So basically electrolytes, okay? What you have is you have strong electrolytes, you have weak electrolytes, or you have something called non-electrolytes. Now, Dr. Burns, I think, okay, the bottom one should be non-electrolytes, okay? My interpretation of the way he's got his, okay, instead of weak electrolytes for the third block, it should be non-electrolytes. All right, so let's look at these for a second, okay? So let's look at sodium chloride, for example, okay? If I take sodium chloride, okay, you all know it dissolves in water, right? It ionizes or disassociates, okay? So if I put it into water, okay, it makes sodium ions and then chloride ions. And they're floating around in water, okay? Do those ions conduct electricity or not? Okay? The answer is yes, very well. And they, caution you not to sit in the tub and have an electric iron in there or something, or a radio, because if it falls in and it's plugged into the socket, then the electric current charges the ions and you get fried. Okay? It usually doesn't work out for the person in the tub very well. Okay? So that material, okay, acts as an electrolyte. So salts, soluble salts are electrolytes. Strong acids, okay, hydrochloric acid, okay, you put it in that water to make hydrogen ions plus the chloride ions, or HCl aqueous, okay, is a good electrolyte. It'll conduct electricity. So if I took this little apparatus that he's got right there, plugged it into the wall, threw in some salt or threw in some hydrochloric acid, that light would light up. Okay, the textbook does a nice little job with the demonstration. Okay, and you're actually going to do this in lab. So a soluble salt is a strong electrolyte. A strong acid is a strong electrolyte. A strong base is a strong electrolyte. For example, sodium hydroxide. Again, you put it into water and it creates sodium ions and hydroxide ions, NaOH aqueous, and it will conduct electricity. Strong electrolytes. Anybody know how many strong acids there are? Okay, there are 7 strong acids. Okay, and basically they're the hydrohalic acids, so the HCl, the HBr, the HI. Okay, those are all strong. HF is not. Okay, HF is a weak acid. So halide group 7. Okay. Also strong acids would be H2SO4, HNO3. What's HNO3? Nitric acid. Okay. HClO3 and HClO4. Anybody know the name of these two? This one's called chloric acid. It's one of those oxo acids. Okay. And this one's called perchloric acid. Okay. Those are the 7 strong acids. Every other acid that you might run into in chemistry is a weak acid. So I tell my folks, we're on the 7 strong acids, every other acid's a weak acid. It's easy to figure that out, okay? Not too hard to understand that. Anybody know the strong bases? Anything in group 1. So the lithium hydroxide, sodium hydroxide, potassium, rubidium, okay? Anything in group 1. And what I call the heavy group 2. Usually from calcium down. Calcium hydroxide, strontium hydroxide, barium hydroxide. Those are all strong acids. Strong bases. Every other base is a weak base. Okay? Ammonia is considered to be a base. It is a weak base. So if I take a soluble salt, has you talked about solubility rules? Okay, a couple people shaking their head, a couple people not sure. Okay, if you have a soluble salt, then it's considered to ionize completely. Okay, if you have a strong acid, it's considered to ionize completely. If you have a strong base, it's considered to ionize completely. 100%, that's the blank that's there, 100%, those are all strong electrolytes. If I throw them into a container of water, if I have electrodes, if I plug that electrode in, that lamp will light up good and bright. You will do this as a demonstration in lab, okay, to verify this. Strong electrolytes. Second block talks about weak electrolytes, okay? Second block talks about weak electrolytes. So, here's all these hydrohalic acids, hydrochloric, hydrobromic, hydroiodic, okay? People say, oh, HF, that belongs there. No, hydrofluoric is a weak acid, okay? Hydrofluoric is a weak acid. Basically what happens is the hydrogen ion and the fluoride ion have a equilibrium reaction, a double-headed reaction, make HF aqueous, but it's only about 10% ionized. Usually the weak acids and the weak bases are somewhere in the range of 10% or less ionized. So would you consider that light bulb to light up real bright or just dimly? It'll light up dimly, okay? It'll light up very dim. So weak electrolytes, if something doesn't ionize, okay, or it ionizes to just a small extent, all of the weak acids, all of the weak bases are considered to be weak electrolytes. They ionize to about 10% or less. That's the blank on your page, about 10% or less. Weak acids, weak bases, and the very low soluble salts. And then the last thing on that page, the last block, is your molecular molecules that don't ionize at all, okay? Anybody know the name of this compound? Bunch of college students, you ought to. Okay? This is ethyl alcohol, okay? It's just drinking alcohol, okay? Drinking alcohol, while it will mix with water, it's miscible with water, okay? Because you usually don't drink 200 proof alcohol, okay? It's usually watered down, okay? It does not break into ions, okay? So this is a non-electrolyte, okay? So if I put that in a solution with those two leads and that, looking for that lamp to light up, would that lamp light up? The answer is no. It doesn't break down into ions. It's a non-electrolyte, okay? Sugar, C12H22, what is it, 12 or 11? 11, okay? C6H12O6. Sucrose, glucose, fructose, all those toses, okay? All those sugars, they're all molecular compounds. They will not break down and they will not conduct electricity, non-electrolytes, okay? So their ionization, their percent ionization is really 0% because they're not breaking down. So I can take sugar water, okay, throw it in that little apparatus. Is that light bulb going to light up? No way. If I take pure water, distilled deionized water, weak electrolyte, strong electrolyte, or non-electrolyte? Non-electrolyte. It doesn't appreciably break into ions. If I got tap water out of the tap back there and tried that experiment, you think that light would light up? Huh?
Dimly.
Very dimly, because the local municipality, whether they're on Lenore City Utilities or Knox Utilities, adds stuff to the water, mainly for your teeth, okay, fluorides, chlorides and stuff, and